Hello everyone, myself Monu from group number 322. Today our topic is mechanism, work and energy. Work introduction: work, potential energy, kinetic energy and strain energy. We have seen that we can gain an insight into the force and stress involved in many biomechanical systems by using the equation of statics equilibrium alone. However, if we we are to study problems that involve dynamic action such as running and jumping, we shall need to develop additional techniques. One of the most powerful tools available to use is the principle of conservation of energy. Energy is a scalar quantity with SI unit of joule. Joule are derived unit equivalent to Newton meters. We should not confuse energy with moment or torque, which are vector quantity whose magnitude also happen to be measured in Newton meter. The concept of work is similar to that of energy. We usually associated energy with a body and work with a force. In this chapter, we shall concern ourselves only with mechanical energy and not with other forms such as heat energy. The work done by a constant force action on a body is equal to force multiplied by distance moved in direction of the force. If the force and the distance moved are taken to be a vector, then the work done is their dot product. By definition, therefore, a force that produce no displacement does no work. In a conservative system, all the work that is done on the body is recoverable from it. In some sense, it is stored within the body as in form of energy. Potential energy is associated with the potential of a body to do work under the action of force. In order for a body to have potential energy, it must be subjected for a force. Potential energy can perhaps best be understood by considering the work done by the force acting on the body. The work done by the force is equal to the potential energy lost by the body. The weight of a mass in gravity is mg. In order to lift the mass from one strain to another, we would have to do work on the body. This work could, however, be recovered if we allowed the body to fall back to the lower step. The work that would be done by the gravitational force during the process of falling would be the force time the distance moved, or work equal to mgh. We might therefore consider that the body has more potential to do work or potential energy when it is on the top step relative to when it is on the bottom step. Obviously, we can choose any position as the reference position. The potential energy can only be relative quantity. Kinetic energy is associated with the motion of body. Newton's second law tells us that a body subject to a constant force will accelerate at the constant rate. The work done by the force on the body is converted into kinetic energy of the body. The kinetic energy K of the body mass m travel at velocity v is uh, K equal to half mv square. Strain energy is associated with the deformation of the body. If the deformation is elastic, then all the strain energy is recoverable if the load is removed. The strain energy in a bar can be defined in terms of the area under the load displacement curve. You can see diagram. Uh, Once again, the energy of the body can body can be calculated from the work done by the force acting on it. In this case of the force is not constant but is applied gradually, so that particular value of the force is associated only a, with an increment of displacement. Using the above definition, potential energy and kinetic energy are terms that we might use in studying the dynamic of rigid particle. Deformable body have strain and energy as well as potential energy and kinetic energy. When we applied the principle of conservation of energy, we tactile assume that all the work done to a body is converted into a force of energy that can be recovered. In some situations this is not true, and the energy is converted into form that we cannot recover. The most common example include plastic deformation and friction force. When a bar is bent beyond the elastic limit, it suffer permanent deformation, and we cannot recover the energy associated with the plastic deformation. Indeed, if we wished to restore the bar to its original condition, we would have to do work on it. Similar, when a body is pulled along a rough surface on the through a fluid, we must do work to overcome the friction force, which we can never recover. System in which the energy is not recoverable are called non-conservative. Sometimes particular in associate assessment of problem in fluid dynamic, we might modify our equation to cater for an estimate in cover energy loss. Uh, we should not always regard non-conservation system in a negative light. If, for example, we need to absorb the energy of an impact, it might be most appropriate to use a port system that dissipates the energy using the viscous characteristics of the fluid. Cars are designed with zones that absorb energy in gross plastic deformation. Unfortunately, they can only be used once. Our next topic is uh, application of the principle of conservation of energy. Uh, Gravitational force on the body, falling and jumping, and the reader will be familiar that with the calculation of the velocity of rigid body falling under the action of the gravity. The principle of the conservation of energy dictated that the sum of the potential and kinetic energy is constant. In that case, the strain energy is negligible. Here, consider a body of mass m drop from a height h under the action of gravity. Mm, Change in potential energy, this and change in kinetic energy, in delta k. For conservative system, delta u plus delta k. We can we can extend the principle to estimate the force applied to the body during falling and jumping action. Consider, for example, the case of a person dropping from a wall onto level ground. There is a three-stage process. There is a period of free fall during which potential energy of the body is converted into kinetic energy. The feet hit the ground and the reaction force from the ground doesn't work to arrest the fall. The energy stored as plastic strain energy in the bones and muscles during the arrested process will be released, causing a recoil effect. The first two stages of the process are indicated in figure 1.29. Two possibility are illustrated in the first. um, the knee are locked and the body is arrested rather abruptly, and in the second, the knee are flexed to give a gentler landing. We can apply the principle of conservative of energy from the time at which the fall commences to that at which it is arrested and the body is again stationary. At the both of these time and the kinetic energy is zero. The work done on the body by the reaction of the ground must therefore be equal to the potential energy that the body has lost in the falling process. We have an immediate problems in that we do not know how the reaction force change with time during the arrested process. The second problem, landing on a bank knee, is addressed in section 1.9. The method adopted could produce unreliable result for the first problem because of the difficulty in estimating the dynamic compression of the skeleton. An alternative approach would be to take the legs as a spring, with the compressive force being proportional to the displacement and the equate the strain energy in the leg at the end of the resting process with the potential energy lost by the body. Thank you.